Hello everyone. In this video we are going to see about the subject control system, unit 3, frequency response and system analysis. In that the topic is compensators. Objectives. At end of this video we gain a knowledge for analyzing the various methods for frequency response as well as the stability of the systems. Compensators. Before we are going to see about the compensators and their types and then working, first why we are going for compensators, in what cases we are using compensators. First of all, the control systems are designed to perform specific task. The task in the sense it is related to accuracy, relative stability and then speed of response. In time domain, the transient state performance specifications are given in terms of rise time, maximum overshoot, settling time and damping ratio. But in the case of frequency domain, the transient state performance are in terms of phase margin, gain margin, resonant peak and then bandwidth. The first step in design is the adjustment of the gain to meet the desired specifications. In practical systems, adjustment of gain will not be sufficient to meet the given specifications. So in such cases, it is necessary to introduce additional devices or components in the systems to alter the behavior as well as to meet the design specification. Such a redesign and addition of a suitable device is called compensation. That is called compensators. A device inserted into a system for the purpose of satisfying the specification is called as compensators. Generally, the compensators introduce a pole and zero in the open loop transfer functions to modify the behavior of the systems. The compensation schemes used for feedback control system is either cascaded combinations, it is otherwise called as series compensations, and the next one is parallel compensations, or it is otherwise called as parallel combinations or parallel compensations. The first diagram representation is series compensations, that is the compensator with the transfer function Gc of S is placed in series with G of S with plant. And in the second diagram, in feedback compensations, the signal from some element is feedback to the input and the compensator with Gc of S is placed in the resulting inner feedback path. So the series and parallel compensator schemes are shown in the figure respectively. Then the choice between the series and then the feedback compensations depends on nature of the signals in the system and the power levels at various points, components available and then designer's experience, economic considerations and so on. Generally, the compensators may be electrical, mechanical, hydraulic, pneumatic or other type of device or network. Usually, an electric network or electronic device serves as a compensator in many control systems. And also, different types of compensators are available. What are they means? Generally, compensators are of three types. That is, first one is lead compensator, lag compensators and then lead lag compensators. In control system, compensation is required in the following situations. What are they means? When the system is absolutely unstable. Unstable. So if the system is unstable means then compensation is required to stabilize the system as well as to meet the desired performance. But if the system is stable means the compensation is provided to obtain the desired performance. Then where we used compensators, where we used a lead compensator, and then where we used a lag compensator, and then where we used a lead compensator means if the control system with the type number 2 and above means we are absolutely, that is the system is absolutely unstable system. Hence for the system with the type number 2 and above, that we require lead compensators, because the lead compensator increases the margin of stability. So next we are going to see about in detail about the lag compensators. So generally lag compensator is an electronic circuit having the characteristics of a lead network is called a lead compensators. If a sinusoidal signal is applied to the lead network, then in steady state the output will have a phase lead with respect to the input. The lead compensation increases the bandwidth, which improves the speed of response. Also, it reduces the amount of overshoot. Generally, lead compensators appreciably improves the transient response and stability margin, and also increases the system error constant by limited range. Generally, lead compensation is to make an unstable system as a stable system. And then one more point we have to know about in the lead compensator is a generally high pass filter. So it amplifies only high frequency noise signal, as well as if the pole introduced by the compensator is not cancelled by a 0 in the system means then lead compensation increases the order of the system by 1. So these are all about the lead compensators, and then importance of lead compensators. And then lead compensator have the transfer function of the form Gc of S equal to S plus Zc divided by S plus Pc. Here the Zc is the 0 of the control systems, and then P is the poles of the control system. Here the zeros can be represented as, in some systems it is denoted as capital T, that is time constants. Here we are using the constant tau. Tau is nothing but a time constant, divided by S plus 1 divided by alpha tau. Always alpha value is less than 1. Here pole is located left of the 0, that is 0 near the origin. This is the main difference between our lead compensators and then lag compensators. Next, lag compensators. Lag compensator is an electrical network. It is usually have the characteristics of a lag network. That is, if a sinusoidal signal is applied to a lag network means then in steady state the output will have a phase lag with respect to input. Lag compensation generally results in large improvement in the steady state behavior of the system, but it results in the slower response. Why means it is due to reduced bandwidth. The attenuation due to lag compensator will shift the gain crossover frequency to a lower frequency point where the phase margin is acceptable, as well as the lag compensator will reduce the bandwidth of the system and will result in slower transient response. Generally, we have already seen that lead compensator is a high pass filter, so it only amplifies the high frequency noise. But here lag compensator is the low pass filter, so high frequency noise signals are get attenuated. Then lag compensator increases the order of the system by 1, in which case means if the pole is introduced by the compensator we have added to the control system means it is not cancelled by a 0 in the system means, and that case it increases the order of the system by 1. So the lag compensator have the transfer function of GC of S equal to S plus ZC divided by S plus PC. Here as it is, the 0 can be represented as 1 by tau, but the pole is represented as 1 divided by beta tau. Here the beta value is always greater than 1. Here pole is located to the right of the 0, that is pole is near the origin. It is the only difference between the lag compensator and the lead compensators. So these are all about the lag compensators. And the third case is lag lead compensators. Here the lag lead compensator is the combinations of lag compensators and then lag compensators and then lead compensators. Here the compensator having the characteristics of both lag lead network. In a lag lead network, when sinusoidal signal is applied means both phase lag and phase lead occurs in the output, but it occurs in the different frequency regions. Phase lag occurs in the low frequency region and phase lead occurs in the high frequency region. That is, phase angle varies from lag to lead as the frequency is increased from 0 to infinity. Then what are the characteristics of lag lead compensators means? It is basically increases bandwidth and speed ups the response and decreases the maximum overshoot, as well as lag compensation increases low frequency gain and thus improves the steady state accuracy of the systems. So at last, the lead lag compensators combines the advantages of lag compensators and lead compensations. Lag lead compensator possesses 2 poles and 2 zeros, so such a compensation increases the order of the system by 1 unless cancellation of poles and zeros. And then the S-plane representation of the lead lag compensator having the transfer function of the form GC of S equal to, the first one is representation of lead compensator and then second one is representation of lag compensators. So it can be represented as 1 plus 1 divided by tau 1 divided by S plus 1 divided by alpha tau 1. It is a representation of lead compensators and then it is a representation of lag compensators. So always the alpha value is less than 1 and then beta value is always greater than 1. So these are all about lag lead compensator characteristics. Next, design of lead compensators. In the design of lead compensators, what are the specifications we are assumed means to meet the design performance means system error constant and then the phase margin. Step 1. First determine the loop gain K for what means to satisfy the specific error constant. In the steps 2, using this value of K, we have to draw the magnitude as well as the phase Bode plot. How we draw the magnitude and the phase Bode plot means first determine the phase margin and the gain crossover frequency. If phase margin is not satisfactory means design lead compensator. Next, determine the phase lead. How we determine the phase lead means we have a formula phase lead pi L equal to pi S minus pi P M1 plus epsilon, where here pi S is a specified phase margin. It is a specific case of epsilon. If we have 5 degree means it is slope near gain crossover frequency and it has minus 40 dB. If it has 15 to 20 degree means we have minus 60 dB per decade. And in the step 4 we have to determine the alpha parameters. How we find the alpha parameter means, here alpha equal to 1 minus sin pi m divided by 1 plus sin pi m. If pi m is required more than 60 degree means, it is recommended to use two identical compensators. For what means, to contributing the maximum lead to phi L divided by 2. And in the step 5 we have to find the gain in the unit of decibel. How means, just we have to take 10 log of 1 divided by alpha, and at last we have to compute the two corner frequencies, omega 1 and then omega 2. Omega 1 can be found out by omega m into square root of alpha, and then omega 2 can be found out by omega m divided by square root of alpha. At last, draw the magnitude and the phase plot of the compensator system, and as well as check the phase margin. These are the steps to be followed in the design of lead compensators. Next, as of now we have designed the phase lead compensators. Suppose we have to design the lead compensators and then it can be added to the control system means, what are the effects after we are adding to this control system means, it adds the poles and zeros to the forward transfer function. It also adds more damping to the system. Then rising time, settling time reduces. It improves the phase margin and the gain margin, and the bandwidth of the system will be increases. In turn, the bandwidth increases means the steady state error cannot be affected. Next, now we are going to solve one problem related to lead compensators. First, the question is, design a lead compensator for a unity feedback system with an open loop transfer function g of s equal to k divided by s into s plus 1 for the specifications of kV equal to 10 and then pi m equal to 36 degree. How we approach this problem is, first we have to find the step number 1, that is we have to find the gain. So how we find the gain means, that is we have one formula, kV equal to limit s tends to 0 s into g of s equal to 10. Wherever we have s means we have to substitute 0 means at last we have k equal to 10, that is the gain value. In the second step we have to substitute in the general transfer functions, that is k divided by s into s plus 1. In replace of k we have to substitute the value of 10. And then second step we have to find the transient sinusoidal transfer functions. How we find the sinusoidal transfer function means, wherever we have s means just we have to substitute j omega, that is 10 divided by s. In the place of s we have to substitute j omega into j omega plus 1. How we find the phase margin pi means, minus 90 degree minus tan inverse of omega. How means we have the general formula for phase angle. And then the given question, the gain crossover frequency is minus 3.3 radian per second, and then phase margin is 17 degree, and then substitute this in the lead phase means 36 minus 17, that is our phase margin, plus phi equal to 24 degree. Then we substitute the value of pi m in the formula of alpha. We have one formula alpha equal to 1 minus sin pi m, that is 24 divided by 1 plus sin 24. At last we get 0.4217. After that we have to take the magnitude contributions. How we take the magnitude means, just we take 10 log of 1 divided by alpha. At last we get 3.75 dB. From the Bode plot we have 4 radian per second. In the last step we have to find the corner frequency omega 1 and then corner frequency omega 2. Omega 1 formula is omega m into square root of alpha, and then substitute 4 into alpha value is 0.4217. At last we get one corner frequency at 2.6. And then second corner frequency have to find using the formula omega m divided by square root of alpha. Then we substitute the value of omega m4 divided by square root of alpha. We get a value of 6.16. Then at last we have to substitute these values in the transfer functions. Therefore the compensator transfer function is the general compensator transfer function is g of s equal to 1 plus tau s divided by 1 plus alpha into tau s. We get 1 plus 0.385 into second divided by 1 plus 0.162 seconds. Therefore the open loop transfer function of the lead compensator system is gc of s into gf of s. That is general compensator transfer function and then feedback compensation functions. So in the questions we have find the 10 divided by s divided by 1 plus s, and then gf of s can be represented as 1 plus 0.385 seconds divided by 1 plus 0.162 seconds. And then you have to find the phase angle, means pi equal to tan inverse of b by a in the numerator, means b in the sense 0.385 seconds, minus in the denominator we have one pole at origin, so minus 90 degree, and then minus tan inverse of omega, and in the third functions we have tan inverse of the b by a. Here we have b value is 0.6. These are general representations we have already seen in the polar plot. At last at omega equal to 4 means, that is frequency 4 means, we have a phase angle of minus 144. At last the phase margin is 38 degree. So this is the one way of approach to in the case of a lag compensator problem. At last we have to see about the difference between lead and lag compensators. What are the difference between phase lead and lag compensators are? Here in the lead compensators, bandwidth increases. The bandwidth increases in the turns, gain increases. In the lag compensator, bandwidth decreases. Here phase lead compensator, dynamic response is faster. Here dynamic response is slow down. Here it is susceptible to high frequency noise, but lag compensator high frequency noise is totally suppressed. No significant decreases in steady state error in the case of lead compensator. Here totally the steady state error is decreased. Where we are using lead compensator means wherever we have required fast dynamic requirements, means that time we have to prefer the lead compensators. Wherever we required low steady state error means that time we are using lag compensators. When which cases the lead compensators and lag compensators are not applied means when phase angle of is decreasing rapidly near the grain crossover frequency, means that case we are not using lead compensators. And lag compensators cannot be applied when which case means uncompensated system, that is phase angle in low frequency region is not sufficient to provide the phase margin, means in that case we are not preferred lag compensators. So these are all the differences between lag compensators and then lead compensators. And then next, so these are the reference I used to make this video effective for your purpose. Thank you all.